All right, welcome to the deep dive. Today we're going to be talking about something that's pretty fundamental to how we make sense of the world around us. Visual representation, specifically when it comes to data.
Absolutely.
We always hear that saying, a picture's worth 1,000 words, right?
Right.
And when it comes to data, that is especially true.
Definitely.
Because, instead of trying to wade through like these huge tables and spreadsheets, just endless rows and columns of numbers, graphs, a really good graph can just immediately show you, give you a sense of what that data is really telling you.
Yeah. You just get that intuitive understanding of it much quicker with a visual representation than by just looking at numbers.
Exactly.
Absolutely.
So in this deep dive, we're going to be focusing on 3 specific ways that data is visually represented, all based on the materials that you shared. We're going to be looking at bar graphs, we're going to be looking at histograms, and we're going to be looking at frequency polygons.
Yeah, three very common and very powerful ways of representing data.
Exactly. And we've got some great examples here that not only show us how these graphs are actually constructed, like how do you actually make these different graphs, but more importantly, how do you read them?
Yeah, how do you interpret them?
And what can you learn from them?
Exactly.
So this is going to be like your key, I think, to unlocking the stories that are hidden within data.
Absolutely.
Because we see data all the time, like everywhere around us. Whether you're looking at, like survey results or trying to understand trends in the market or just generally trying to be more informed about, the world around you. Getting comfortable with these visual tools is going to be a huge asset.
Yeah, for sure.
Okay, so let's unpack this, starting with something that I'm sure everyone is familiar with, or at least has seen at some point in their lives. We're going to be starting with bar graphs.
Okay.
So take it away. Tell us about bar graphs.
So bar graphs are, at their simplest, a really easy way to compare different categories of data. So you have these bars, and all the bars are the same width, and they're equally spaced apart. And one axis, typically the horizontal one, will list out the different categories that you're comparing. So this could be something like different months of the year, different types of expenses, whatever it is you're looking at.
Right.
And then the height of each bar will correspond to the value or frequency of that category on the other axis of a vertical axis.
Okay.
So it's a really intuitive way to just visually see, oh, this category has a higher value than this category.
Right. Right. And we have a great example here in the materials. It talks about a survey of 40 class IX students.
Okay.
And they were asked about their birth months.
Okay.
And so if you look at figure 12.1, you can see that it's presented in the form of a bar graph. And, just glancing at that, how quickly can you tell which month had the most number of births in that class?
Yeah, you immediately see which bar is the tallest, which month has the highest frequency.
Exactly. Exactly.
Yeah. And that's the real power of the bar graph. It just makes it so obvious.
Exactly. You could immediately compare.
Yeah.
Okay. Now, example 2 gives us another example of how this works in the real world, I think. It talks about a family with a monthly income of 20,000 rupees.
Okay.
And then it lists out their planned expenditures under various heads. So it talks about groceries, rent, education, medicine, fuel, entertainment, and miscellaneous. It's all laid out in table 12.1. But then figure 12.2 takes all of that information and puts it into a bar graph.
Yeah, which really brings it to life.
Exactly. And so what can you tell immediately from just looking at that bar graph?
Well, you can immediately see where they're spending the most money.
Right.
Where their biggest expenses are.
Exactly. Which ones are the highest, which ones are the lowest.
Yeah. You can see that Ent and education are their 2 biggest expenditures. They're both at 5,000 rupees.
Exactly. And then you can even compare, medicine is 2,000 rupees. But education is more than double that.
Yeah.
And it's just so much more apparent when you're actually looking at it visually.
Absolutely.
Versus just looking at the numbers.
Yeah, it just makes that comparison so much easier and quicker for you.
Exactly. And this is why bar graphs are so great for this kind of comparison between, distinct categories.
Yeah, when you have separate categories that you want to compare, bar graphs are a fantastic way to represent that data.
Perfect.
Okay.
So now that we have a good understanding of bar graphs, I think it's time to move on to something that's a little bit different but related. Histograms.
Okay.
So what makes histograms different? When would you use a histogram instead of a bar graph?
So histograms are like bar graphs in that they use rectangles to represent frequencies, but they're used when you have continuous data that's been grouped into what are called class intervals. So things like heights, weights, temperatures, things that fall on a continuous scale.
So instead of separate categories like grocery or rent, we're talking about like ranges, like you said, like weights between 30 and 35 kilograms.
Exactly, exactly.
Okay.
So for example, in table 12.2, you can see the weights of 36 students, and they're grouped into these intervals, like 30.5 to 35.5 kilograms, 35.5 to 40.5 kilograms, and so on.
Right.
And then figure 12.3 shows us the histogram for that data. And the one thing you'll notice right away about a histogram is that there are no gaps between the bars.
Oh,
It's one continuous block.
right, right.
And that's because we're dealing with continuous data, right? So one weight range flows directly into the next.
Okay, so it's visually showing that connection between the different data points?
Exactly.
Okay, I see that now.
Yeah, so that's one of the key visual differences between a bar graph and a histogram.
Okay, and I see here that it mentions the width of the bar is significant in a histogram, whereas it wasn't really with bar graphs. Why is that?
Well, that becomes particularly important when we start talking about histograms with varying widths, which can get a little more complex. But even with uniform widths, the area of each bar represents the frequency of that class interval. So when all the widths are the same, it just means that the height is also proportional to the frequency, so it's easy to interpret.
Got it. That makes sense to me. So now this is where it starts to get a little bit trickier. I think example 3 is a good illustration of this. It talks about marks in a math test, and the marks are grouped into these intervals. And the thing is, the intervals are different sizes.
Okay.
So you've got like 0 to 20, and then 20 to 30, and then you go all the way to 60 to 70. But then it jumps to this really wide interval of 70 to 100.
Right.
And it says here that the initial histogram that was drawn, which is in figure 12.4, is potentially misleading.
Yeah.
Why is that?
The reason it's misleading is precisely because those class intervals are different sizes.
Okay.
So if you just draw the bars with heights corresponding to the frequencies in that table, table 12.3, the bars for those wider intervals are naturally going to appear larger, even if there aren't proportionally more data points within that range. So, for example, the 70 to 100 mark range has a frequency of 8 students,
Okay.
whereas the 60 to 70 mark range has 15. But because that 70 to 100 bar is so much wider, it could visually suggest that more students scored in that range than actually did.
Right.
Right, so it can be a little bit deceptive if you're not careful.
So just because a bar is wider doesn't necessarily mean that the frequency is higher, because the interval itself is also wider.
Exactly.
So how do we correct for this? How do we get a true representation?
Well, that's where we have to introduce the concept of frequency density.
Okay.
So to accurately represent the data when the class widths are different, we need to adjust the heights of those rectangles so that the area of the rectangle is actually proportional to the frequency.
Right.
So the way we do that is first we identify the smallest class size,
Okay.
which in this case is 10 marks. You can see that in those 20 to 30, 30 to 40 intervals.
Right, right.
And then we essentially adjust the height of every other rectangle to reflect the proportion of students per 10 marks interval.
Okay.
So you're basically standardizing it
Got it.
to that smallest class size.
Okay, so let me just make sure I'm understanding this correctly. So like if you look at table 12.4, for the interval of 0 to 20, the width is 20,
Mm-hmm.
and the frequency is 7. So to get the equivalent height for a width of 10, what they did is they took 7, they divided it by 20, and then they multiplied it by 10, and they got 3.5.
Exactly.
So they're basically figuring out how many students there would be in a 10-mark interval within that 0 to 20 range.
Yeah, assuming an even distribution.
Got it. Okay, that makes sense.
Mm-hmm.
So if you look at the corrected histogram in figure 12.5, you can see that those wider intervals now have proportionally lower heights.
Right.
So it gives you a much more accurate visual picture of how those students actually performed.
Yeah, it takes away that misleading aspect of those varying widths.
Exactly.
Mm-hmm.
And the area of each bar is now actually representative of the frequency in that class interval.
Yes.
This is so important,
It's really crucial.
especially when you see histograms with those unequal bar widths. You know, You can't just look at the height. You have to look at the area.
Exactly. The area tells the true story.
Exactly. Okay, great. So we've covered bar graphs, we've covered histograms. Now it's time for our third type of visual representation, frequency polygons.
Okay.
So what are they?
Frequency polygons are another way for us to visually represent quantitative data and their frequencies.
Okay.
And they're particularly useful when we're dealing with continuous data. And what's interesting is that they can often be derived from histograms.
Oh, okay.
So if you look back at figure 12.3, the histogram for the students' weights, if you were to find the midpoint of the top of each of those bars
Mm-hmm.
and then connect those midpoints with straight line segments, you would essentially be creating a frequency polygon.
Oh, okay. I see that in figure 12.6.
Exactly.
They've labeled those midpoints B, C, D, E, F, and G,
Mm-hmm.
and then they've connected them. And it also looks like they've added points A and H at the beginning and the end.
Yeah.
Why is that?
Well, those are added to essentially close the polygon.
Okay.
So we assume that there's a class interval with 0 frequency before the first actual class and after the last class. And by connecting the polygon down to the horizontal axis at their midpoints, you essentially make the area enclosed by the frequency polygon equal to the area of the histogram.
Oh, interesting.
And then the reason for that has to do with properties of congruent triangles, as the text hints at.
Oh, wow. Okay, that's a really cool connection between the two.
Yeah, it's a nice little geometrical links between them.
I like it. So it seems like you can also draw a frequency polygon directly from a frequency distribution table. You don't necessarily need to make a histogram first.
That's right, you don't have to.
Okay, how would you do that?
So to do that, we use what are called class marks, and those are simply the midpoints of each class interval.
Okay.
And the way you calculate them is very simple. You take the upper limit of class interval, you add it to the lower limit, and then you divide by 2.
Oh, okay. So for our weights example, for the range 30.5 to 35.5 kilograms, the class mark would be 35.5 plus 30.5, divide that by 2, and you would get 33.
Exactly.
Okay, got it. And then you would do that for every single interval.
For every single interval in your data set, yeah.
Okay, and then you plot it, I'm assuming, on the axis.
Exactly. So you plot those class marks on the horizontal axis, you plot the corresponding frequencies on the vertical axis, and then you connect those plotted points with straight line segments to form your frequency polygon, just like when we derived it from the histogram.
Right, okay. And I think we have a good example of this in example 5.
Mm-hmm.
It talks about the weekly cost of living index. And so table 12.6 gives you the index ranges and the number of weeks. And then in table 12.7, they've calculated those class marks.
Mm-hmm.
So for 140 to 150, the class mark is 145.
Correct.
And so they plot those points, 145.5, 155.10, and so on. And then they connect them. And again, they add those extra points with 0 frequency at the beginning and at the end.
Exactly, yeah.
Okay.
You always need those 0 frequency points to complete the polygon.
Got it.
And to make sure that the total area under that polygon is representative of the total frequency of your data.
Okay.
And one of the really neat things about frequency polygons is that they make it really easy to compare 2 or more sets of data on the same graph.
Oh, how so?
So you can just plot multiple polygons on the same axis, and the shapes of those polygons and their positions relative to each other will immediately tell you how those distributions compare.
Oh, that's really helpful.
Yeah. So let's say you was comparing the results of 2 different surveys that you conducted.
Mm-hmm.
A frequency polygon would be a really nice way to just see at a glance. Are those distributions of responses similar, or are they different?
Yeah, and like question 7 in the exercises even talks about comparing the runs scored by 2 cricket teams.
Exactly. So you could plot those runs scored over a certain number of balls. You would have 2 separate frequency polygons.
Mm-hmm.
And you could immediately see, oh, this team tends to score more runs in this range of balls, or this team is more consistent, things like that.
So you can really start to see those patterns emerge.
Absolutely.
Okay, great. So we've looked at bar graph, histograms, and now frequency polygons. And we've talked about how they're all, really useful for representing different kinds of data. And now the material that you sent, it also has this whole exercise 12.1, which is filled with real-world examples of how these are used. Should we take a look at some of those, maybe?
Yeah, let's take a look at a few.
Okay, so question 1 talks about a survey on the causes of illness and death among women.
Okay.
And a bar graph would be perfect for this
Yeah.
because you could have the different causes, reproductive health conditions, neuropsychiatric conditions, and then the length of the bars would just immediately show you their relative impact.
Exactly. You'd see, okay, this cause is a much bigger problem than this cause,
Right.
just based on the length of those
Yeah,
bars.
you'd see that relative scale.
Yeah, absolutely.
Okay. Question 2 talks about the number of girls per 1,000 boys in different sections of Indian society.
Mm-hmm.
And again, bar graphs, I think, would be a really good way to represent this as well.
Absolutely, because you're comparing different categories, right?
Right.
Scheduled caste, scheduled tribe, rural, urban.
Exactly.
And so the bar graph will let you very quickly see how those numbers compare across those different groups.
Okay. Question 3 talks about election results. So, like, the number of seats won by different political parties.
Yeah, that's a classic bar graph example,
Yeah.
right? Because you have your different parties, and then the height of the bar shows you how many seats they won.
Exactly. And, questions 4 and 5, they talk about, one of them is about leaf lengths, and the other one is about the lifetimes of neon lamps. And both of those involve continuous data.
Mm-hmm.
So those would be good examples for histograms.
Exactly, yeah, because you're looking at the distribution of those measurements across a range.
Right, exactly. And then questions 6 and 7 both specifically mention using frequency polygons to compare the performance of two sections of students, and then the runs scored by two cricket teams.
Mm-hmm.
So, just looking at all these examples, it really does show just how versatile these tools are.
Yeah, they have so many applications, and I think it's great that we're highlighting that.
Absolutely. Okay, so as we wrap up our deep dive today, what would you say is the key takeaway, like the one thing that you want our listeners to remember?
I think the key takeaway is that bar graphs, histograms, and frequency polygons are really powerful tools for understanding and comparing data.
Absolutely.
They allow you to make quick comparisons, they reveal the distribution of the data,
Mm-hmm.
and they can highlight pattern that might not be obvious if you were just looking at the raw numbers.
Right.
And I think the key is to remember which type of gram is best suited for which type of data.
Okay, yeah, so remind us again.
So bar graphs are best for discrete categories.
Right.
Histograms are best for continuous data, but you got to pay attention to those interval widths.
Yes, very important.
And then frequency polygons are also good for continuous data, and they're particularly useful when you want to compare multiple data sets.
Right. Okay, perfect. I think that's a really good summary.
Yeah, I think so.
So, yeah, I think these visual aids really do make it so much easier to understand what the data's telling you.
Absolutely.
Like, they can reveal insights that you might just totally miss if you're only looking at the numbers in a table.
They turn those numbers into stories, basically.
Yeah, exactly, like a visual narrative. Okay, so final thought for our listeners. The next time you see a graph, I want you to think about what kind of graph it is.
Mm-hmm.
Think about what kind of data it's representing and how that choice of graph is affecting the way that you're interpreting that data.
Yeah, and think about if a different type of graph might tell a different story
Exactly.
or reveal something new.
Yeah. Okay, well, that's all the time we have for today's deep dive. Thanks for joining us.
Thanks for having me. It was fun.
Yeah, it was great.